I'm Irwin. I'm here to talk about a project of continuum analytics, which is called DyND. So the title of the talk is, sorry?
Can you speak a bit louder?
Yeah, sure. So the title of the talk, or I can, there's a microphone.
There are no speakers.
Okay, so I'll just speak louder. The title of the talk is DyND, Enabling Complex Analytics Across the Language Barrier. And one of the things that DyND has been engineered to do is to be a kind of NumPy-like library, but not for just for Python, but also for other things like R and JavaScript and Julia potentially. So that's where this title comes from. And so I've split this talk into two parts. The first is let me just exit that. Screen, yeah. Okay. So the first is the what and why of DyND. So that's going to be DyND at a high level. We're going to talk about why it exists, why we're doing it, what we're doing. And the second is I'm just going to show you some code snippets of the kinds of things it can do. So what is DyND? DyND aims to be a modern library for array-oriented computing. Okay, great. What does that even mean? So what that means is DyND is a library. It's not a language. So I mean, many of us use arrays. Many of us, I think, use NumPy. I mean, I'm just curious, how many people have used NumPy? Everybody? Yeah, exactly. So we do those kinds of calculations. NumPy is quite old now. It's at least 20 years old, as Travis said. It started, the origins of it were really 1997. It's got a lot of sort of flaws and sort of other things we'd like to do that would be nice if we enabled. So DyND is a library, like NumPy, that we hope will help people do these things. It is not a language into itself. That is something that's sort of a solution like Julia, which is also very good, but a bit different. So this helps do computation with arrays. And when I said it's a modern array-oriented library, what I really mean there is that we're using software engineering practices from today trying to solve problems that people have had for a while. I mean, I don't know if you've ever looked at, I'm sure most people here haven't looked at the NumPy source code, but I mean, even Travis would agree with this, that it perhaps wasn't as well engineered as it could have been at the time. So what is DyND really? DyND is really a collection of three things. It's a fully featured type system along with a callable like function object together with an array container engineered in C++ and bound to dynamic languages like Python. So we have type objects, we have a callable object, and we have an array container. And we've written these completely in C++, and then we want to bring them to other dynamic languages. So before I go any further, I just want to be clear about what DyND is not. DyND is not NumPy 2.0, whatever that may mean. So NumPy is really good at what it was designed to do originally, which is basically computations with broadcasting and sort of stride-based manipulation. It's extremely good at that particular thing, and you won't get a lot of improvement on those particular areas. It's the other areas, which some other tools like DyND and the other kinds of tools that Travis were talking about, where we might see improvements. And NumPy is the kind of thing that may not even be replaceable. I mean, Fortran, is still extremely widely used, and it's very old. DyND is not a JIT for Python. That's Numba. So if you have arbitrary Python code and you want to make it faster, you should look to Numba. That's something that Travis just talked about. And this may not mean much to perhaps this audience, but DyND is not something like, it's not a C++ library like Boost multi-array. It's not template-based. It's dynamic. So we do use templates, but they are hidden detail. But to users, you will only ever manipulate dynamic objects. Okay, so you may think it's 2016. Why write another array library? And the answer is, as I've said, because there are problems that are not being otherwise solved. So let me give you some examples. So one example is missing data. So if you use something like R, you can have data which may or may not be present. It may be optional. If you use something like Julia, they have a similar thing, which is a nullable type. Why can't we have something like this in Python? In NumPy, there's this concept of masked arrays, which is kind of like a halfway house for this. It's not, there is overhead related to these masked arrays, and NumPy is not always consistent with how it treats them, and they're not really stored in the best way possible. So we really should have a missing data solution in Python. A lot of data scientists would like something like that. This is something that's been discussed for years. I mean, if you look at the NumPy mailing list, you can find Like, I kid you not, like an 100 email thread about this in 2011, which just went on forever about the different ways to do this, and then no one did anything. So DyND, this is one reason DyND exists of many. One of many reasons is that this is something that we've implemented in DyND that does work today. So if you want an array container with proper missing data semantics, you can find it there. Here's another example, variable length strings. NumPy can't represent strings of different lengths well. It can represent strings of a fixed length. If you want to have arrays of strings of only size 4, it can do that. If you want arrays where strings may be different lengths, it can only do that through Python objects. So that's really not great. And I can show, and an example here I've shown is suppose I have an array of strings of say length 4, and I create it using the NumPy string size 4D type, and I do a copy of that. That takes 2 microseconds per loop. If I try and do it with variable length strings and just do a copy, it takes 40 microseconds per loop. So you're getting like a factor of 20 slowdown just trying to use variable length strings in NumPy. That shouldn't be the case. Our array container should be able to support variable length strings efficiently. Strings are a very common thing that people want to do. So that's another thing that we've put into DyND that we feel is a problem that people have faced. Another example is custom types. The NumPy D types are too primitive, so they're good for representing extremely basic things like floats or integers. But how do you represent something like categorical data? Categoricals are just you have a variable and it may take one of a preset number of values. Or what about something like a ragged array? What about so in that case my dimensions may be they may have different sizes. I may not be operating in some sort of square or cube. It might be jagged. Or GPU data. It would be nice to be able to, naturally be able to represent these things in NumPy without having to like rewrite NumPy because if you're a user, you just don't have that option. Another example is we should be able to define overloads on NumPy functions. If you're using a programming language like C or C++ or Julia or many other things, you can very naturally write a function which operates on a particular set of types. Why can't we do that in NumPy? And that is, for instance, string concatenation. You might want to overload the plus operator to combine 2 strings. It's a very natural thing to do that happens in many languages, but we can't do that with something like NumPy. And that is, again, something that we've tried to solve in DyND. And my last example here would be that a lot of the times we just don't want to use Python. A lot of the time we do, obviously. Python's great, and if it's the right thing to use at the time, you should do so. But you may just, it may be easier to express your computation in R. Or you may just really need to work at the C++ level for whatever reason. I mean, programming is really about expressivity. So you should go to the language where your data is and where you can express the computation the easiest. And DyND aims to be that solution where you can have a common way to represent data and functions across languages. Right. So 4 general traits of DyND that I'm going to talk about a little bit is I feel DyND is expressive, generic, extendable, and pluggable. And I'm going to give you specific examples of how it is so. So expressive. So actually, Travis had a very similar slide here. DyND's type system is something called datashape. And datashape is actually the type system shared across most of the Blaze ecosystem with continuous various other projects. And this is a structured data description language. The key difference from something like NumPy is that the dimensions and the D type are combined into the type. So whereas NumPy has the shape and the D type, we've just combined them all together. So I have examples here. So for instance, we might have a dimension type, which we call var, which means variable size dimension. And it may have a D type that's a 32-bit integer. Or we may have a D type, which is a string, and we may have 3 of them. That's a fixed dimension. And we also have things like struct types, which is an aggregate type with different kinds of data and labels for what the names are. And we can represent tabular data in datashape with a dimension type like var in front of the child type, which in this case would be something like the struct or record type. So the point is that this type system is much more expressive than what you can get in NumPy, and you can express a lot of a wider variety of data that you may encounter in the wild using it. So I also feel DyND is generic. So we have these 3 objects I mentioned earlier, which is that we have this type, this callable, and this array object. And these are simply reference-counted smart pointers in C++. And if you don't know what that means, it doesn't matter. That's just, but if you do know what that means, that's sort of like modern C++. And these dynamically interpret data. So you can just use these things. You can create them with different types. You can manipulate them. And it's almost like a sort of like a highly specific and efficient dynamic object that you'd see in Python, but written in C++ and then bindable to other languages. The types can be parameterized on the types. So you can, very easily write a generic thing which operates on a particular, on arrays that are of a fixed size. But where, for this example, I'm using this t, but you take in an arbitrary d type. Or option, which is how we represent missing data. So I can very generically write an array function which operates on anything that has missing data. And callables, for how we work with callables, which are array functions, we think about them in a functional sense, which means that we want you to write an innermost operation and then use predefined transforms to get the exact array computation you want. So maybe you want something that does broadcasting, or maybe you don't. Maybe you want a reduction. Maybe you want some sort of windowing function like the kind Travis talked about. And the idea here is, here I've shown an example of an Elementwise, and this is C++, and I will show you Python and C++ sort of interchangeably as we go. Here, you can just very simply write your innermost array computation, and then with a single line, get something that can operate on any number of dimensions very specific to what you want to do. And I'll show more examples of that. So DyND is also extendable. So types and callables are first-class objects that users should create directly. And I've given an example of this here. This is just a C++ class. I'm not going to go through this in detail, but the point is I want to show you that it's very easy to just go write your own custom type, define a few sort of standard functions which DyND needs to know about to understand the data, and do operations with it. Likewise with callables, if you don't want to use our predefined transforms, if you really need to do something extremely custom, you can write your own callable, which knows how to interpret and manipulate the array data. So we're sort of not hiding anything from the users. Every tool we use internally in DyND to create DyND is something that is available to you. So there's nothing hidden, no sort of layer of detail that you can't get access to if you need it. But most of the time you shouldn't need it, but it's there if you do. So DyND's also pluggable. I think this is something interesting, which we haven't talked about much before. DyND supports plugin libraries. So when we were building it, we've been thinking about what about if someone comes along and maybe they're maybe they're writing games, maybe they're doing data science. Doesn't matter what they're doing, but they want to write some specific callables or types for their needs, and they'd like them to be propagatable to the other languages DyND supports, which for instance Python is. So you can write today you can write a DyND plugin, define your custom array operations. You can use particular functions in DyND, for instance, ndset. So you'd write your callable, here it's f. You'd do ndset with the name and the callable there. Or you could do a namespace of callable. So you could give a list of callables and names. And if you just did that at the C++ level, it would propagate the whole thing to Python automatically. You would not have to write any sort of custom Python code or boost Python code or anything. So you can actually simply just write these array operations at the C++ level and get them in Python without any extra work. So that basically halves the amount of code you have to maintain because you don't have to maintain any sort of wrappers. And that's dynamic. Right. So this brings me to the second part of the talk, which is just want to show off simple examples of DyND in action. So I'm going to talk about the different kinds of types and show you code for them. I'm going to talk about some of the functionals and how to create different kinds of array computations. So again, just to remind you, in DyND, types are instances of simple classes. So if you write a class, then you can get a type, or obviously you can use all the ones that we have already existed, that we've already created in DyND, like integers, floats, strings, different kinds of dimensions. Types also can expose dynamic features to arrays. So the idea here is that you should never, ever have to subclass a DyND array, which you can always just propagate behavior to it using types. So you can propagate methods through the array using types. You can define how the data is interpreted using types. So an example here is something like complex numbers, which would define properties .real.imag, which are, if you know what a view is, they're views on the data. And you can also define a function like conj, and that can all be done dynamically. And you can do this for your own types. And types can also be abstract in DyND. So you can have kinds that match a whole family of types, like int or scalar or fixed, which matches dimensions, or any, which matches anything. And you can also, there are also patterns. So if you want to write, as I showed a few examples earlier, so you might want to write a data shape which is a fixed times some particular d type, but it's parameterized on t. You can do that. The last example I have here is that's what a callable signature looks like in DyND. You can take any arguments. You can actually also take keywords. And you can also write this sort of in this sort of abstract notation if you want, or you can write it very specifically with the exact types if you want. DyND also has metadata and data. So the metadata in DyND is something like the strides in NumPy. It is what you use to describe the data. So it's a bit lower level than the data shape. So it actually is like a low-level data shape. And but the difference here is we've generalized it so that rather than just be about the strides, it can describe other things. So you might have some particular tuple. So you might have a tuple which is an int, a float, and a string. So there you'd put the byte offsets into the metadata. You wouldn't do that. DyND does that, but it is there. You might actually be representing a pointer, and you'd put some of the information about that into the metadata. Or in this ragged array dimensions I've talked about earlier, there's other different kinds of metadata. So the point is that the metadata is a generalization of how we describe the data beyond just the strided approach in NumPy. And array data is also poolable or allocatable in custom memory spaces. And we've actually done this to support GPUs. We just do this sort of generically, but so we have a way to talk about data which is in a different memory space which requires custom operations. So, and that fits very naturally with the CUDA model. Right, so just some simple examples of code here. So these are fundamental types. So just showing you how to create an integer or a string or a float. These are very natural things that you would do. Or the last example here, which is a string, which is the variable length string I talked about earlier, which DyND sort of natively supports. We also have dimension types. And in DyND, there are two basic dimension types. The first is a fixed dimension. That's sort of what you'd expect from NumPy. So it's a fixed size. It can't change. And it represents that. And the second is a variable size dimension. So in the first example here, I'm creating a size 3 array of int32s. And in the second example, I'm creating a 2D array, which is just a 2x3 array. So it's not that exotic. And in the third example, which is a little bit exotic, I'm creating a variable size dimension array. So the inner dimension here is var. And you can notice that I'm initializing it with 3 lists. The first list is 1, 2, 3. The second list is 4, 5. And the third list is 6. Right. So that does not have uniform dimensions at all. And DyND can represent that naturally and operate on that naturally. So I think that's also something that people have sort of wanted to use for a while, but there may not have been an appropriate solution in the NumPy space. We can also support aggregate types. So these are just things like tuples and structs. And again, these are the kinds of things that come up a lot if you're doing data science. So in the first example, I'm creating an array of just a tuple, so an int, a float, and a bool. And in the second example, I'm creating a struct, which is just like a tuple, but it's got names for the members. So I'm creating a bool, an int, and a string with certain names. And you can access them using those names. And with a tuple, you access them using the index, so 0, 1, or 2. And we also have missing data represented using an option type. And so here, we use the question mark in front of the d type to indicate optionness. And in the first example, I'm creating an array of size 3 and using none to pass. Python indicates missingness using the none value. And DyND understands this as NA, which is sort of the same sort of semantics R uses, if you're familiar with that. And what we do, which is different from something like pandas, is that we represent the missing data using sentinel values, which are specific to the particular type. So pandas will just typically convert everything to float and then represent it using nons. But in DyND, we actually have an integer-based solution or a string-based solution or whatever. And that can extend very naturally to custom types as well. We also have symbolic types. So in DyND, we have, as I said, we can have variables like t to represent a parameterized type. We have ellipses, which can represent any number of dimensions, like in the second example. And we also have any, which is just an sort of like the superclass type. And we have a type matching. So when you call a DyND function, it will try and match the input types against the signature. And you can see here that my type of fixed times t matches 12 times int16. Or my type of fixed times t does not match var times int16. So it's just a dynamic thing that it's a dynamic matching of the same kind that you'd get in something like C++ or compiled language, which would check it at compile time. So we also have callable and functionals in DyND. So DyND is not just about data, it's about expressivity and compute. So in DyND, you can share the callables just alongside data. So the callables are first-class objects that can go between languages. And I showed an example of that earlier with this dynamically publishing callables using ND set. So we want people to write a callable in one language and bring it to another. So you should be able to write a callable in C++ and bring it to Python without doing any extra work. And we also want to enable the creation of callables using generic patterns. So we have a bunch of functionals which transform one callable to another. And I will show examples of them, like Lwise or reduction or multi-dispatch or outer or neighborhood. All the kinds of things that, that fit a variety of computations. And our callables are also overloadable. So you can actually define particular operations like plus, minus, multiplication, divide, whatever, for your own custom types, which you can register. So here's an example of an Elementwise functional in Python. We use decorators here to indicate a functional transform. If you're going to write a callable in Python, you have to specify the output type. And that is because DyND needs to know what to allocate. That's a very natural thing. NumPy, for the cases where there is some overlap, NumPy also has to do something similar. It needs to know what to allocate. So you can't just write you can't just write a Python function with no return. And what we're using there is Python 3 syntax. There's an equivalent Python 2 thing if you don't want to use Python 3. But Python 3 actually supports annotations like that using the arrow. And it can also support annotations on the input types, but we haven't used them there. So there I've written a simple function which returns a float 64, and it's just 2x plus y minus z. And if I use the Elementwise decorator, it will automatically transform this into an array function which takes any number of dimensions. And I can print out the signature here, which is the first argument becomes a bunch of dimensions times a scalar. The second argument also a bunch of dimensions times a scalar, and so on. And the return type is a bunch of dimensions times a float, as I specified. And then I can then apply this to any sort of number of dimensions, or if I just want to throw Python objects into it, lists of lists or whatever. Similarly, we have a reduction functional. So there I'm just doing a maximum of two numbers, and we're returning an int32. And then I apply the reduction functional decorator, and it becomes a little bit more complicated, but not that much so. So the first argument, again, just becomes a bunch of dimensions times a scalar. And then I actually get keyword arguments, which DyND supports. So we can take in a bunch of the axes over which to do the reduction. We take in the identity element, if there is one. The question marks here mean that those are potentially optional arguments to the function. And we can take in an argument called keepdims, which is just whether or not I want to keep all the dimensions of size 1. These are the same sort of things that NumPy has. And we return a bunch of dimensions times int32. And you can see I can do the reduction on a list of 6 elements, and it returns the maximum. And below, I pass in a keyword saying, hey, I want to do this reduction, the maximum, but use 101 as the identity, and then I get 101 back. So it's just, the point here is that with a single line of code, you can get very simple array computations that are of the kind you want. And you can use for something like Elementwise, you can use any number of arguments. We can also write multi-dispatch functionals, and here's a simple example. Multi-dispatch, by the way, if you don't know, is when you just want to write something which has different behavior for different types. So an example would be something like the gamma function, which is a function used in science and engineering. And what's special about this is that on integer values, it reduces to the factorial. But if you don't have an integer value, it's much more complicated. So here I've just thrown up a simple example where I've written a factorial function and a gamma function. So the factorial is for integers, the gamma is for real numbers. I can then use DyND's functionals to sort of stitch them together. So totally different behavior, but you want the abstraction but under the same abstraction. So then once you've stitched them together, you don't have to think about it, you can just call it, and it'll branch depending on what's going on. And then on top of that, I've put it into the Elementwise decorator, so I will apply this across any number of dimensions. So this creates, the callable is just takes in a single array, returns a single array of any number of dimensions of any scalar. And I can apply that to various kinds of data, and it does the computation as expected. So for integers, I get integers back using the factorial. For floats, I get floats back using the gamma function. Option operations, so again, like for missing data, you can just show here that we already support the built-in operations on missing data. So I can, add a non-missing value to a missing value, and you will get either propagation of missingness or skipping, depending on sort of keyword values and what operation you're doing. So in the second example there, I'm creating an array of missing data and subtracting an array of no missing data, and I get missingness propagated appropriately, so on and so forth for the rest. And a very cool feature of DyND, which I haven't talked much about today, is that because we support things like variable length arrays, and because we support things like strings well, and because we support these things like structs, we can actually very natively represent JSON-like data. So I can create, ragged structs of whatever, and then I can do operations on it, which are simply impossible in NumPy or many other of sort of similar solutions. So here, I've created a list. So I have 3 people, Alice, Bob, and Charlie. They each have some credits. And I want to know who is sort of like in debt. So what this is a variable length array. It's a fixed array of structs, so strings, and then within one of the members of the structs is a variable length array. So it's a bit complicated. So 3 structs, and inside the struct is a variable length array, which could be whatever, it's variable, any size. And you see that because these guys have different number of credits. And then, so I set up that data, and then I can very naturally do the same sort of computations I might want to do in NumPy, but on this very exotic data set, which is I just want to know who's out of money. So I'm going to sum the credits, and I'm going to ask which is less than 0, and I want the name. And in one line, I can get that very easily. In this case, it's both Bob and Charlie. So I'm actually out of time now. So that's good, because I'm finished my talk. I want to thank a few people. So the core contributors, which is me, Mark Wiebe, Ian Henriksen, and Stefan Krah, all of whom are excellent, all of whom come from very different backgrounds. And we also have a number of other people, too, to thank. I also want to thank Continuum. Continuum has very graciously been funding this project, and many others. And you should check out all their stuff, including many of the things I just mentioned. And yeah, I also want you to try DyND. DyND is still, a bit experimental. It's certainly a lot less experimental than it used to be. So I'm not going to say, everything works smoothly, but I think you can do a lot with it now. And I encourage people to play around. I encourage people to use Conda to install it. That should work. And yeah, and thanks for listening. How do we store strings? Right. So we have 2 strings types. One is a fixed string, which same as NumPy, so that kind of makes sense. Yeah. And the other one, it's a pointer and a size with a special optimization for small strings, where we store them inline. So we store an array of pointers and sizes. So for each string, there will be a pointer and a size. But if the string can fit into the combined bytes of that pointer and that size, it will do so. There's a small optimization for that. That's similar to what things like Spark uses.
So I guess that is my next question is then, so there's the whole arrow and feather stuff now.
Yeah.
Which uses contiguous, store strings contiguously.
Right. So.
Are you trying to be compatible with that, or is that?
Right. So that's a good question. So to speak to arrow and feather, so I think I almost had a slide on something like this, but then I decided not to do it. But so I think there are sort of 2 projects, which are, if you want to say what is similar to DyND, there are 2 things I would list. One is Julia, and one is yes, arrow and feather. And I'll touch on both of these right now. So Julia is a whole language, and I think if you look at sort of, and obviously much broader scope, much more mature, much more contributors than DyND, clear. DyND is sort of like, I think DyND and Julia share a lot of the same philosophy and a lot of the same underlying design with the type system with regards to how they treat arrays. So I think there are a lot of similarities there, which is interesting. For arrow and feather, That is a data frame specific approach. So if you want, and actually like arrow also doesn't actually have any compute. So that's another difference. So we're compute, yeah, Travis.
Is it possible to express the arrow description as a data shape?
Yeah, absolutely. So that is, one could, and that's sort of the point of something like data shape and DyND, is that we want people to be able to write types which can represent all different kinds of data, and an arrow data shape would be something very natural to do. So arrow doesn't have any compute, and is only for data frames. So if you have something which is not a data frame, it just doesn't, that's not a thing it does. Yeah. So DyND in that sense is more general.
There would be a data shape description of the arrow format.
Yeah.
That's the way I would characterize the relationship.
What's the integration with NumPy like? Could I start using this now in my NumPy project
Yeah.
and use U-funcs?
Yeah, so the NumPy integration is actually pretty good. And in fact, Stefan Kra, who works on this, is the buffer maintainer. And Mark Weep also has written a lot of NumPy as well. So it's extremely good, I would say. Yeah.
Can you go back to the factorial example?
To which example?
The
Factorial. Yep.
Actually, the functional example.
This one?
Yes.
Okay.
So if I understand correctly, when you're writing on an array with these functionals, it's actually calling back Python calls on code. So every inner loop is converting back
Right.
and forth.
So I extracted over a few details here. So and the answer is no, that's not what we're doing. But so if you write your call, you can write your callables in either C++ or Python. If you write them in C++, then you're in C++ land and things. Okay, fine, great. If you write them in Python, actually what we're doing here is we're using numba underneath to JIT it. I just haven't explicitly shown that. So if numba is present, it will JIT that. If it's not present, then yes, it will do exactly what you said. But that's, I mean, yeah, but I mean that's what you get from writing something in Python. We can't really make that.
To work with NumPy, it makes more sense for Python users using NumPy than for.
I would totally say that, yes. Yeah, but it does work without numba if for whatever reason you're in an environment where that's not there. But if you want to write something efficient in Python with DyND, yes, you should use numba alongside. You should have it installed.
How does search speed compare with boost multi-array?
How does search speed? So it's not something I've ever looked at, but it's a good question. But I don't have an answer for you. Yeah, yeah. I mean, multi-array is it's a template-based array library, and the point when I mentioned earlier that I want to make is that while we may use templates, they're like a hidden level of detail, and that if you use C++ DyND, it's just like manipulating simple dynamic objects. Whereas Boost, it's all templated.
Is it possible to share functions like this that you can find in Python with the languages?
So that is something, the answer is it should be possible. It's not something, we haven't gone beyond Python yet. We'd like to hit R and potentially even Julia or Java or Node or something like that. This is not something we've got to yet. But yes, the idea is that is like a primary goal. And the fact that we're sharing functions between C++, like all of DyND is written in C++ and then shared naturally to Python, that's sort of like an early stage proof that we can do that.
Following on from the question, do you have an idea of roughly how that would go in terms of the implementation? Like I prefer writing mine in Python, but I work with friends of mine who are in R.
Yep.
It would generate some sort of library that they would be able to import into
Right.
R and that kind of thing.
Right.
Fine.
So the answer would be like, so I think I showed a slide earlier on about DyND plugins.
Yep.
So you'd write a simple plugin library, which would just be a shared object library. And DyND will, if DyND Python is there, it will know how to deal with that and bring your callables to DyND Python. If DyND R is there, which doesn't actually exist, but if DyND R is there, then it will know how to interpret that and bring your callables to R. That's one way to do it, yeah.
How are missing values implemented?
Yeah.
And would DyND be suitable if you have quite sparse data?
Right, yeah. So good questions. Missing values. So right now they're implemented using Sentinel values, which is the same technique R uses. So for every particular type of data, you have to say, this is the particular value I'm going to use to represent missingness. And for missing values, to be honest, there are multiple approaches, and they all have like advantages and disadvantages. So that Sentinel approach I just said has some particular advantages, like it can be more efficient in some cases, but sometimes you may want like flags. And ultimately, we actually intend to support both. Your second question, which is about sparseness, DyND absolutely would be suitable for something like that. We don't have a particular sparse type yet, which is probably what you'd want. But it's been, that's one of the things we're thinking about. One of our developers is an applied mathematician and thinks about that a lot. Yeah.
So you're making
So, yeah.
That kind of implies generally that your code's going to do a lot more kind of iffing and fussing and it's not going to optimize as much. Have you done speed comparisons on
Right.
these regular shape things?
So I would actually say it's not, yes, of course, we are making something more flexible than NumPy. We're trying to fill in the gaps, is what I would like to say about that. In terms of, whether there'll be like a lot more branching or a lot more, so what we've done is because we've focused a lot on optimizing things like multi-dispatch, so you can get very quickly to the particular code you need for your particular operation. And yes, for that we have done benchmarks. And what we do there is we actually use something like Google's hash map library, which is extremely fast and can look up something in just a couple of nanoseconds. And if you're at the C++ level, that is extremely fast. Like I have timed this, an empty function call in Python, just like lambda : none, takes like 40 nanoseconds. So that's when you do a couple of nanoseconds, it's almost negligible for the kinds of computation we're talking about when we're talking about arrays. Does that answer your question?
So have you done any speed comparisons against NumPy?
Yes. So specifically against NumPy, yes. So for something like, say, a basic arithmetic operation, you would not expect to beat NumPy. You should match it. I mean, NumPy would be very well optimized for that if you're just talking about adding two numbers. And we typically do match it, yes. And for some of our GPU stuff, we actually have benchmarked against PyCUDA. And again, we typically do match it. But I'm not saying these are comprehensive, but I'm saying, yes, we have done benchmarks.
There's no reason it has to be stored.
Yeah.
It's not more general in a way that it has to be stored.
OK, great. Oh.
You said there's Python bindings for a C++ core. Does it apply to everything? Like is everything that you showed here on the Python layer, is that available in C++ as well?
Yes, everything. In fact, there's actually more in the C++ layer than in Python, because that's the whole point. The binding should be as shell as possible. So yes.
And the other question I had was for serialization. If I want to send DyND objects over the wire, is there?
Yes. So there is a work in progress on that. There is some code. It's not something that people should use now. We have an extensive design document about how that's going to happen, and it's well thought out and well planned. It's just someone needs to sit down and finish it. Yeah. So yes, that's very much a thing that's happening. Yeah.
And these design documents, are they open?
Yeah, they're all open. So if you go to the DyND GitHub, which is, or you just go to libdyn.org, which links to everything, you'll find links to this. And on our repository, we have like a dev docs folder with all that. Yeah. So we have a lot of good design docs there. Some slightly out of date, but yeah.
So as a corollary to what you said earlier, because you showed the multi-dispatch, well actually on this slide, yeah. So basically you have a multi-dispatch functionality for C++.
That's right, exactly. And then we figure out how to, if things can be brought just straightforwardly to Python, we do that. And in some cases, we might change the syntax a bit to make it more natural with the particular language. Because I want Python users to feel like they're writing Python, for instance. Yeah.
So there is no more question then. Thanks, Zaid, again.
OK, thanks.